All right, so you should have plotted your parent function. We talked about why we're using these values. So I'm sure you guys have the right points plotted, and then make sure you understand what's happening with your function. So when we plotted these points, 1, 2, 3, 4, 2, and 9, 3, the function looks like this with an arrow here. It will continue to the right because I can keep plugging in higher positive numbers and still get a square root. But at the end, this is an endpoint. So this is something you guys haven't seen yet in the different functions that we've graphed. They always went infinitely in both directions. And this has like a distinctive endpoint, like literally the graph stops here. You cannot plug in anything past this point. It just stops at this one point completely, okay? So if we went through and tried to look at some of the characteristics of this graph, for our parent function, the h and the k are 0, 0 because there's no transformations in that graph. That also happens to be the x-intercept and the y-intercept of the parent function, which we've seen happen often, just due to the way that they're structured. So what is the domain of this function? Look at the graph. What is the domain? Emily? Good. Okay, so looking left to right along the x-axis, the graph has that distinct endpoint at 0, but it does have graph to the right of it. So you have to use x values that are greater than or equal to 0, or in interval notation, that means from 0 to infinity. All right, what about the range of the graph? Beverly? Good. Okay, so because again it has that distinct endpoint and we're looking up and down, we're looking at y values now, and y has to be greater than or equal to 0. Or in other words, the same interval from 0 to infinity. Now if you're on this graph from left to right, as we look at increasing or decreasing intervals, okay, so the graph doesn't start till here. And then when I move towards the right, like I'm reading the graph from left to right, here's what I'm doing. Okay, so increasing or decreasing? Increasing the entire domain, okay? That doesn't mean everything from negative infinity to infinity because the graph doesn't go that far. It means from 0 to infinity. And you can remember with increasing, decreasing intervals, we don't pay attention really. They haven't defined fully whether the endpoint needs to be included or not. So it doesn't matter whether you say it like this or like this, okay? Those mean different things. This means this includes 0, and this one means it doesn't. But they haven't really like dived into, it's not important enough for them to determine whether you want to include that in the interval or not include it, okay? And then for the decreasing interval, there's none. Is the function 1-to-1? Yes. Okay, so it's a function. It passes the vertical line test. It also passes the horizontal line test, so it is 1-to-1, okay? These things are not applicable, rate of change or axis of symmetry. Minimum value. What's the lowest value that this graph hits? 0. What's the highest value that this graph hits? Right, it's infinite, so we say no maximum value, okay? None. And then asymptotes are not applicable for this function either. So what I'm actually going to do, since the transformations work out the same, is I'm going to do one example of the transformations for you guys to remind you in case some people have forgotten about them. And then we're going to do the cube root parent function together because all the same ideas will apply but with a new parent function. And then you guys are going to spend the rest of the period working on the other problems for cube root and square root that we haven't done in their characteristics. And we'll make sure that either on Canvas or when you walk in tomorrow, the answers are there for you to check for your Cartesian catalog. Does that make sense to everybody? Okay, because you guys know how to do this stuff. I do want to give a small reminder, like I said, in case we forgot a little bit about transformations, but then I don't think it's as fruitful for me to stand up here and go through them when it's something you guys are capable of doing, okay? So for the one example I'm going to do the harder example. When I say the harder example, I get that it's all relative, like the Algebra 2 trig version of the square root problem. So the front side you see is the same as what we do in Algebra 2. On the back side is where we have an Algebra 2 trig problem, okay? And that's just because there's a b value inside of that function, okay? So remember when there is a b value in the function And when I say B, if you don't even know what I'm talking about when I say that, like it was a long winter break and here we are, okay? Remember, we're comparing it to this type of setup. So if I want my function to look like that, I just kind of need to separate the -2 from the rest of the function, okay? And for those of you before, if you're like, I don't get why she has us do this B value thing, I could always take it out of like the squared or out of the absolute value. If you didn't get it with greatest integer, that there are some places you can't take it out because in greatest integer, we couldn't just factor it out. Here's another place. If you separate this into the square root of -2 times the square root of x minus 2, you don't know the square root of -2 in real numbers, so you can't simplify it in real numbers to get anything on this graph, but this is a graphable thing. So this is a place where we need to understand how that b value affects the graph. And so then if you guys remember looking at this, notice that there's no a value written here, which means the a value is still a 1 like it is in the parent function. And there's no k value, which means it's still a 0 like it was in the parent function. That means my vertical parts of my graph are not changing at all. They're going to stay at the same place as the parent function. So remember, we want our parent function to compare it to. So hopefully you have this on the other page, but you kind of understand why we picked different numbers than we normally do for the square root. And then we're going to do some stuff to the x's, but the y's are staying unchanged. Okay? Specifically because there's no a or k value. Now remember, the vertical stuff is easier to change. Its behavior acts just like the value you see in the equation. If there were a 6 out here in front of the radical multiplying the function, I would multiply y by 6. If there was a plus 10 here at the end of the function, I would take y and I would do plus 10. Okay? It's the horizontal stuff that's a little bit trickier. Okay? So horizontally, we have kind of 3 things happening. We have this multiplication by a negative, this b value of 2, and this minus 2 from x over here. Okay? Now, the b value is -2, and the negative is causing one kind of transformation, and the 2 is causing another. But remember how we've studied this. The 2 in the equation means something in the equation, but it means something slightly different than what we measure on the graph. The horizontal distances are not actually doubling. By doubling the value in the equation, the horizontal distances are actually getting cut in half on the graph. Do you guys remember that? That we use the reciprocal of that. So my x distances are going to get multiplied by -1/2. So if I had a 1 before that was 1 unit away, that will now be reflected negative, and it will only be half a unit away from the 0 point that I was measuring it from. Then we have an h value in here, but like it shows in the formula, and like we saw when we've done investigating, subtracting 2 in the equation doesn't actually move things subtracted to on the graph. It doesn't actually subtract 2 and move them to the left. Instead, having a -2 in the formula is actually like having an h value of +2, and what we've seen it do to the graph is shift everything to the right. So then I can change the x coordinates accordingly. So each thing is getting reflected, multiplied by a negative. The distance from 0 is cutting in half of what it used to be, and then it's getting shifted to the right too. So if I do that with 0, I get 2. If I plug in 1, I get 1.5. With 4, I get 0. And with 9, I get -2.5. Okay. So if I plot those points, I have 2, 0. Sorry, that's not 2, 0. That's 0, 0. 2, 0, 1.5, 1, 0, 2, and -2.5, 3. Okay. And then you should look at them. Does it kind of make sense for the shape? And then remember what this shape looked like. It had one distinct endpoint and the function was going one way. Normally in our parent function, that endpoint was at 0, 0. 0, 0 has been transformed to the point 2, 0. That's the endpoint. I could keep plugging numbers in this way. Okay. And the reason that it's going the opposite direction of what you expected is because of what? The negative, the transformation there. Okay. You would want to actually plug in negatives when there's a negative underneath the radical, because a negative times a negative would then turn it into a positive. That's why you're seeing plug numbers in over here instead of over here. Okay. Now, the other thing I want to remind you guys of is writing out those transformations. So remember how to name all of these. We said it several times, but just to make sure we've named it correctly. Multiplying x by a negative, every time we multiply by a negative is a reflection over a certain axis. When you're changing x, you're flipping positive x's to negative, negative x's to positive. And so that's going over the y-axis. Multiplying x by 1/2 is taking a distance, cutting it in half, multiplying it by a half and changing it to a new distance that's closer to the axis that you were originally from. So that is a horizontal because it's happening to x. Compression, because multiplying by 1/2 would make the distances closer to 0 rather than further away. And then the +2 is a shift, and it's specifically because it's horizontal is going to go to the right 2. Okay. So that was a little bit review, hopefully enough if you weren't quite recalling your transformations on how to use them. Okay. So the last thing that I'm going to give a parent, and we'll graph it, make sure you guys have that, and then you guys will work on the rest of these things. So for your cube root parent, like we said, this chart up here, so we can plug in negatives, and we would choose 8s instead of 2s because they're simpler to find the cube root of. Okay. And so I'm going to plot those points. And I get something like this. Notice it looks really flat. It's not technically flat, but it's kind of like the square root. It's growing, but not like a quadratic and cubic. When you square things and cube things, they start growing really fast, right? Like 10 cubed is 1,000. That's why a cubic is really steep. But these are cube roots. Just to reach 2, I had to go 8 units over for the cube root of 8 to finally reach 2. How far over would I have to go before I can finally reach 10 in height? 1,000. I would have to go over 1,000 spaces before the cube root of 1,000 would be 10. So is my function technically flat? No. But when I draw it, it's growing very slowly. It is climbing, okay, but it's climbing very slowly. So this end looks like a square root, but slower even, right? A little bit flatter looking. But it has the other side too, because you can cube root negatives. It has this other side as well. Okay. Is this all right with everybody? It's important that you differentiate like a cube root type of shape from a cubic type of shape. They're inverses, so they look really similar. But do you see how fast a cubic grows? I will mark you wrong if you try to take this graph and draw this. Because is that what the graph does? No, it does grow, but it does not grow like that. It grows like this. There's a difference in those end behaviors, okay? How they're behaving. So it's important that you know the difference between them. All right, so you guys can go ahead and you can fill in the characteristics for this, and then you can go through and you can graph square roots and cube roots with their different transformations, fill things in, and I'll walk around for you guys to ask questions.